No satellite is watching your phone. Your blue dot begins as a timing puzzle. GPS is a network of space blocks that broadcast one-way radio messages. Each message says where the satellite was and what time it was when the signal left. Your phone compares that sent time with the arrival time in its own receiver. Because radio moves at light speed, that tiny delay becomes a distance. One distance measurement does not pick one location. It makes a giant sphere of possible places. With one satellite, the phone could be anywhere on that sphere. A second satellite adds another sphere, and the overlap becomes a circle. A third satellite usually reduces that circle to two possible points. One point is usually far from Earth, so the receiver rejects it. So the obvious question is, why do phones still need a fourth satellite? The phone clock is not good enough to agree with atomic clocks in orbit. At light speed, a tiny clock mistake becomes a large distance mistake. 10 nanoseconds already means about 3 meters of range error. 1 microsecond is about 300 meters, enough to move the blue dot across a neighborhood. The fourth satellite lets the receiver solve for position and clock error together. In the equations, the unknowns are x, y, z, and the receiver's time bias. GPS calls these distances pseudo-ranges because clock error is mixed into every one. Now comes the weird part. The signals are almost buried before they reach you. A GPS signal at your antenna is weaker than ordinary thermal radio noise. The receiver finds it by matching a non-code pattern against the noise, like finding a rhythm in static. That code timing gives normal navigation, while tracking the carrier wave can reach survey precision. But the path from satellite to phone is not perfectly clean. The ionosphere delays signals differently depending on frequency, sunlight, and charged particles. A lower atmosphere adds delay from pressure, temperature, and water vapor. Receivers reduce those errors with models, multiple frequencies, and correction data. Those corrections come from the control system on Earth. Ground stations constantly monitor satellite orbits and clock drift. They upload fresh correction data so satellites broadcast better navigation messages. So GPS depends on satellites, phones, and the maintained global ground network. The deepest reference points are even farther away. Quasars. Quasars are so distant that they behave like stable pins for measuring Earth orientation. VLBI radio telescopes use quasars to anchor precise geodesy and reference frames. That helps define where Earth, satellites, and receivers are in one shared coordinate system. So GPS is not a space camera. It is clocks, weak waves, geometry, corrections, and cosmic reference points agreeing.